Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone, welcome to lecture 28, Organic Chemistry 2. Today we will start on chapter 7, carboxylic acids. We will cover naming the carboxylic acids, structural and physical properties of carboxylic acids. Naming the carboxylic acids, common names. Many carboxylic acids have common names that are used frequently in the literature. These names often indicate the natural source from which the acids were first isolated. The common names of some carboxylic acids are for C1 formic, C2 acetic, C3 propionic, C4 butyric, C5 valeric acids, etc. Chemical abstracts retain the common names for the two simplest formic and acetic acids. In the common names, the positions of substituents are named using Greek letters: alpha, beta, gamma, delta, etc. For this one, we have here 4 carbons. 1, 2, 3, 4. On carbon number 4, which is gamma, we have NH2, amino group. So that's gamma amino butyric acids. GABA, naturally occurring neurotransmitter. With common names, the prefix iso is sometimes used for acids ending with CH-CH3 2, iso group, ending with CH, CH3, CH3. This acid C6, caproic acid. Caproic acid with this CH3, CH3, we call isocaproic acid. That's flavoring agent. For the IUPAC names, IUPAC nomenclature for carboxylic acids uses the name of the alkane that corresponds to the longest continuous chain of carbon atoms. The final E is replaced by the suffix oic. So if we have formic C1, we call it methanoic acid. If we have C2, acetic acid, we call it ethanoic acid. The carboxy function and the functional group of its derivatives take precedence in the name over the other groups. Senior carboxylic acid over anhydride, ester, acid chloride, acid amide. They are more senior than nitrile, aldehyde, ketones, and ketones superior than alcohol, thiols, and amines. The chain is numbered starting with the carboxyl group, carbon atom, to give position of the substituent along the chain. So we have here 3 carbons, 1, 2, 3. We name number 1 the carbon of the carboxylic group. So it will be 2-bromo propanoic acid. Common name alpha. So alpha bromo propionic acid. Since we have here chiral center, this carbon is R, so it's R2-bromo propanoic acid. In multifunctionalized carboxylic acids, the main chain is chosen to include other functional groups as much as possible. So for this compound, even though the long chain containing carbon, just only carbons, will be non-noic acid, 9 carbon, but the one here contains two function group, double bond alkene and the carboxylic. So this chain will be much more preferable. And the compound will be 5-butyl hept 6-enoic acid. 5-butyl hept, it's 1, 2, 3, 4, 5, 6, 7. So it's hept. On 6, we have double bond, 6-enoic acid. For this compound, we have two function group. We have C double bond O in this chain, and we have the carboxylic group. That's why 5-oxo 4-propyl hexanoic acid will be a better name than 4-acetyl heptanoic acid. For saturated cyclic acids are named as cycloalkane carboxylic acids. For this one, we have cyclopentane and we have here function carboxylic acid, so will be carbon number 1, 2, 3, and on carbon 3 we have oxo, 3-oxo cyclopentane carboxylic acids. For this one, we have here cyclopentane again, 1, 2, 3. On carbon number 3 we have ethyl group, and on carbon 1 we have here 1 prime, 2 prime, so we have 2 hydroxy. On carbon 1 we have 2 hydroxy ethyl, and the name will be 3-ethyl 1 2 hydroxy ethyl cyclopentane carboxylic acids. Their aromatic counterparts are benzoic acids. In this compound, the carbon attached to the carboxy function gets number 1. So here is 1, here is 2. That will be 2-hydroxybenzoic acid, or we can say ortho-hydroxybenzoic acid. Common name for that compound well known as salicylic acid. If we have methyl group on carbon 2, that will be 2-methyl benzoic acid or ortho-methyl benzoic acid. We call it toluic acid. Common name, toluic acid. Dicarboxylic acids are referred as dioic acid. The straight chain dicarboxylic acid, the parent alkane name to determine by using the longest continuous chain that contains both carboxyl group. So in here we have 2. So that's ethane dioic acid. Ethane dioic acid. Common name oxalic. Here we have 3 carbons. That's propane dioic acid. Maleic acid is a common name. We have in this compound 4 carbons. So it's butane dioic acid. Common name succinic acid. Here we have 5 carbons. It's pentane dioic acid. Glutaric acid. Common name. Here we have 1, 2, 3, 4 carbons. Here double bond trans. So that's trans but 2-ene dioic acid. Or these 2 are in different directions, so we get E. So it's E, but 2-ene dioic acid. Common name fumaric acid. If these 2 groups are on the same direction, it's maleic acid common name, and cis or Z, but 2-ene dioic acid as IUPAC name. The chain is numbered beginning with the hydroxyl group, as we mentioned. Atom that is closer to the substituents, and this number are used to give the position of the substituent. 1, 2, 3, 4, 5, 6. So that will be 3-bromohexane dioic acid. In here we have dioic acid, cyclopentane, right? And the COOH groups are in trans positions, right? So we can say trans cyclopentane 1,3-dicarboxylic acid, or we better to give the stereo configuration on both, so it will be 1R, 3R, cyclopentane 1,3-dicarboxylic acids. For the aromatic analog will be here benzene 1,2-dicarboxylic acids, common name phthalic acid. Draw the structures of the following carboxylic acids. Alpha methyl butyric acid. Butyric means we have 4 carbons. Here we have 4 carbons. Alpha means this one is alpha. Okay, as methyl group. This is the structure. Trans 2-methyl cyclohexane carboxylic acid. So we have here cyclohexane carboxylic acids. Cyclohexane carboxylic acid. It's trans. So if this is up the plane, the methyl should be in the back. All right. This is a methyl. This is a structure. 4-oxoheptanoic acid. Heptanoic acid, 7 carbon. 1, 2, 3, 4. 4-oxo. This is a structure. Phenylacetic acid. Acetic acid with 2, 1, 2. This is acetic acid. Here we have to have phenyl, so that's phenylacetic acid. Name the following carboxylic acids. When possible, give both a common name and a systematic name. For this compound, 1, 2, 3, 4, 5. So the IUPAC will be bentanoic acid. On carbon number 2 we have iodo. On 3 we have methyl, so it's 2 iodo, 3 methyl. Alphabet, that's correct. I, then M. For this one, for common name, we have alpha iodo, beta methyl valeric acid. For this structure, IUPAC will be hept. That's 1, 2, 3, 4, 5, 6, 7 carbons. On carbon number 3 and 5 we have methyl, so it's 3,5-dimethyl hept. 4 we have double bond for enoic acid. On this carbon number 4 we have the senior group, and on 5 we have the senior group on the same side, so we give them Z configuration for this double bond. So the name will be Z 3,5-dimethyl hept for enoic acid. For this compound we have here 1, 2, 3, 4. So it's butane dioic acid. On number 2 we have methyl, so it's 2-methyl butane dioic acid. or we can say 2-methylsuccinic acid. For this compound, 1, 2, 3, 4, 5, so it's pentanoic acid. On number 4, we have amino, so it's 4-amino pentanoic acid. Structural and physical properties of carboxylic acids. Taking formic acid as a model, the entire molecule is approximately planar. The hydride sp2 carbonyl carbon atom is planar with the entire triagonal bond angle. As we can see here is angle between C double bond O and carbon single bond oxygen here is 125.9. The angle between the C double bond O and CH 124. Between the CH and CO 111. The OH bond also lies in this plane, eclipsed to C double bond O. It appears that one of the unshared electron pairs on the hydroxyl oxygen atom is delocalized into the pi system of the carbonyl to form this minor resonance contribution structure. Double bond, and here this will be O minus, O plus. Boiling points of carboxylic acids. Carboxylic acids boil at considerably high temperature than do alcohols, ketones, and aldehydes of similar molecular weight. So ethanolic acid is 118, propanol is almost very close, the same molecular weight, 97, and propanol aldehyde it's 49. The high boiling points of carboxylic acid result from the formation of stable hydrogen bond dimer. So the structure actually of this carboxylic acid is dimer, hydrogen bonded. That's double the molecular weight and doubling the molecular weight of the molecule, leaving the liquid phase and requiring more energy, higher temperature for it to boil. Rank the following isomers in order of increasing boiling point and explain the reason for your order of ranking. Well, 2-vinyloxyethane 1-ol, that's an ether here, and an alcohol functionality in here, and we have alkene functionality in here. Ethyl acetate, we have an ester functionality, and for butyric acid, we have carboxylic acid functionality. We find out the ethyl acetate boils at lower temperature, 77.1. The 2-vinyloxyethane 1-ol can form hydrogen bond. That's why the boiling point is a little bit higher. The highest will be carboxylic acid because which forms 2 hydrogen bonds and boils as a dimer at 163.5. So this will be number 1, highest, and the ethyl acetate will be the lowest. And here is the highest. Melting point. Acid contains more than 8 carbon atoms are generally solids, unless they contain double bond. The presence of double bond, especially if they are cis, in a long chain impedes formation of stable crystalline lattice, resulting in lower the melting point. Melting point of stearic acid 70. For linolenic acid is -5 because of the presence of these two cis alkene functional group. Unbranched acids made up of an even number of carbon atoms have melting points higher than the odd number homologies having one more or one less carbon. This reflects differences in intermolecular attractive forces in the crystalline state. What we call it changes in crystal backing and intermolecular forces are responsible for that. See, here is odd. Heptanoic acid, melting point at -10. Octanoic, even, 16.7. Nonanoic, odd, again lower. Decanoic, even number, increase the number. Undecanoic, decrease the number. So here is even, and what we are saying that the unbranched acid made of even number carbon atom have melting points higher than the odd number, and this is a fact. Solubilities of carboxylic acids. Carboxylic acids form hydrogen bonds with water, and the lower molecular weight acids up through 4 carbon are miscible with water. As the length of the hydrocarbon chain increases, water solubility decreases until acids with 10 carbon atoms are nearly insoluble in water. Carboxylic acids are very soluble in alcohol because the acids form hydrogen bonds with alcohol. Also, alcohol are not polar as water, so the longer chain acids are more soluble in alcohol than in water. Most carboxylic acids are quite soluble in relatively nonpolar solvents such as chloroform. Why is that? Because acid continues to exist in its dimeric form in this nonpolar solvent. Thus, hydrogen bonds of cyclic dimer do not disrupted when the acid dissolves in nonpolar solvent. Which member of each of the following pairs of compounds would you expect to have higher solubility in water? Butanol or propanoic acid? Of course, polarity of propanoic acid is higher than 2-butanol, so propanoic acid will be more soluble than 2-butanol. The solubility of butanol is 27.5 gram per 100 milliliter of water. Propionic acid or propanoic acid solubility is 36 higher, 37 gram per 100 milli. Hexanoic or ethanoic? Of course, ethanoic, because hexanoic has long chain hydrocarbon. So the ethanoic acid will be fully miscible with water, while hexanoic solubility is 1.082 gram per 100 milli of water. See you next lecture.